Thank you, thank you. So I know that we went the same like with you. When you start with Pierre, somebody has to stop us. So.
So in this case, it needs to be me.
Yes.
And thank you very much for a very nice discussion. I also see that in chat there was one more questions, but I need to ask you to move the conversation to the chat.
I will respond in chat.
Yes.
Thank you very much.
And we're going now to the next speaker, Dr. Pierre Madl. And he originally trained in electrical engineering and later in electronics, works in this field as a professional for over 10 years. Intrigued by this phenomenon of life, he enrolled as a part-time student at university in Vienna, Salzburg and Brisbane, which in 2003 earned his master's degree in environmental science within a joint academic program between the Universities Plus of Salzburg and Queensland University in Brisbane. Then he pursued further academic studies in the field of biophysics at Plus when he received his PhD in 2009. Since then, he's a researcher in environmental radiation lab at the institution, and together with a privately operated lab in his privileged position, to convert his expertise gained at Plus into real prototypes. His expertise ranges from tropical marine ecosystem to environmental aerosols. Since a decade, he extends his expertise, which includes the study of ultra-weak photon emissions from biota, as well as the electrodynamics properties of water and its effects on living system. And his topic is Heretics or Pioneers, Viktor Schauberger and Wilhelm Reich, a fresh look. Please, Pierre, you can start.
Oh, thank you, Justina, for this introduction. Actually, you said so much. There's nothing else that I can add. Well, first of all, can you hear me? Is my audio clear?
Yes.
Yes.
We do.
Oh,
Yes.
Great. So, thank you, Romiana. Thank you, Jelena. Thank you, Justina, for hosting this session, for everything that you have done over the last 2 days, 3 days. Therefore, it's a very unique experience, not just on the new technological level that we're doing, but it obviously is still possible to interact heavily using this medium, using this platform. Therefore, well, I'm stunned that it works so nicely, even though sometimes I have some troubles, but this may be my end user approach. So what I'm trying to speak about today is rather more off the mainstream menu, very much off the mainstream menu. And it's because maybe in science we are becoming too much specialists rather than generalists. We're looking so deep into particular aspects and losing the relevance, the wider context of what matters. So going back to history, we find some people that have done a basic, let's say, work in terms of how to grasp the understanding, or try to understand how nature works. And that's the contribution that I'd like to wrap up a little bit on it. So first of all, I have to excuse myself. The presentation would be over 100 slides long, which is impossible to squeeze into 30 minutes. And secondly, I'm only picking up a few topics of the presentation. However, anyone who's interested can access the full presentation that is only dedicated. And let me go to, okay, where is it? Why doesn't, okay. That is only dedicated this time to Viktor Schauberger and not to Wilhelm Reich. So this is the second excuse that I have to add, because working on it, as we agreed with Romiana and Shigeoka back then in Budapest, I said, well, it's an easy thing to do. It's not. It amounted to so much material available that I have to truncate and split the talk. This time we talk about Viktor Schauberger, and next time we talk about Wilhelm Reich. So let me proceed, otherwise I'm losing too much time on that. So the basic underlying principle is the pulsation concept that both people developed. So although, let's say, Wilhelm Reich was kind of clashing completely with the germ theory when he came up with the bion theory. We're not typing into that because it's exceeding today's time slot. He came up with a very essential property. That's the pulsation of biotic matter. And we find it everywhere. We find it in the oceans. We find it even in terrestrial systems, like, for example, this is a slime mold. I want to show it slime mold. And the particular pattern, when it changes, for example, it finds a neutron spot and then it changes. Let me see if we can activate that. Yeah. So it changes the pulsation frequency as soon as you put a trigger, like, for example, this particular trigger. Let me see if we can speed up the video. No, it doesn't allow me to speed it up, but anyway, you can see it's pulsating at a resting frequency. And as soon as you place a trigger on it, it starts to speed up the pulsation. So the pulsation is an imminent property. And this pulsation, now it's the triggering input, and now you can see it's fluctuating literally. I'm not quite sure whether you can see this pulsating property on screen. Can you see that? Just wave with your hands. Can you see that? Yelena, Justina, can you see the pulsation? Okay.
I can, yeah, I can see that.
Perfect, that's it. So let's flip over to the opposite side, the Schauberger. What he observed was also a kind of a pulsation, but he did it on a different aspect. He observed this water, when it's exposed to certain gases, pulsates. So you have a kind of a shrinking property and a swelling property that he assigned. We are currently doing something like we want to see if water exposed to oxygen somehow alters the volume that the system is encapsulated. Why we are doing this? This is ongoing work in George's lab, which you can see at the top right. So why we are doing this? If you look, for example, at this particular video, let's say if I can, so this guy is pouring in water into, he's German, so he's pouring water into a jar, and one is reference and the other one is the experimental control. And in this particular setup, he uses them. He missed the crucial point. He's putting carbon dioxide into the flask and sealing it with a balloon. And then he activates an ultrasonic device, so you can see. So creating a mist. And if you wait a little bit, so you have, of course, probably a temperature-induced effect. So this needs to be studied carefully. Oops, sorry. And what you end up with is, if it comes up, you end up with is that the balloon that's sealing the flask is completely sucked in. You can see literally it's actually now popping up inwards. So there is something observable that Schauberger described as the shrinking effect in the presence of CO2. And we would like to repeat this also with oxygen and with CO2 as well to see if we can simply duplicate this particular experiment. So let me proceed to the next section. What else did Schauberger document? He observed a kind of repetitive, he called it the cycloid spiral space curve. It's a repetitive oscillation that is observable in many ways, and it's related in terms of an underlying principle called fractality. And I would like to get this fractality property a little bit better explained. In this case, he was referring to the planetary motion. This particular animation is not to scale though, so there are some consistent errors in it, but the basic principles are interesting. We have the sun dragging along the planets across the orbit as it spirals along in the solar system, or actually in the galactic branch of our galaxy, the Milky Way. I don't have time to go into deep details of Benoit Mandelbrot's theoretical concepts, but anyway, you can see these basic principles of fractality, the self-similar properties, the scale-free properties of fractal structures. When you look at the Koch curve at the very bottom and how it's building up as you divide them in regular patterns. So you skip the video from that, and you skip all these things, but they can be accessed once you access the presentation and look at the links that are in the notes sections. So Schauberger then studied a little bit more carefully. This was the work done with his son, Viktor Schauberger, Walter Schauberger, sorry, that they tried to study what is the hyperbolic funnel doing. And you can see, but you look at it in details, that the suction vortex behaves fractal, and it has a very interesting dynamics. It's very slow at the periphery and very fast at the center. What does this mean? It means if you take, for example, coffee powder, ground coffee powder, and dissolve it with water, and then see the petri dish above, and flush it through the hyperbolic funnel, you can actually do or perform a depuration effect, a cleansing effect. So the water is suddenly cleansed. How can this happen? That you have polluted water and suddenly you end up with a very fine, clear fraction and a fine accumulated, let's say, dirty fraction. Yeah, but it's obviously possible. It probably has to do with the charging effect. This charging effect with this hyperbolic funnel at the bottom shows that the exit cone of the water that jerks out from the hyperbolic funnel is not linear, it spreads out. And at the bottom image, you can see when you touch it, it's literally affected by the presence of the bioelectric field. A footnote, as you can see, this particular hyperbolic funnel, if you cut it at an inclined angle, you actually obtain an egg-shaped cross-sectional area. This for Schauberger was quite crucial, and we come to this later on, why this matters. So, I don't have time to look into the living water dropper, which is a repetition of Lord Kelvin's gravitational spark engine. But again, you can look this online. So we skip that unless we have time for to look at it in the discussion section. What is more important though is because of this technical motion, let's see, you have the propeller or you have a pump, which is slow, the angular velocity is slow at the center, very high at the periphery. You fractionize the water in such a way that if you crystallize it and you look at it under the electron microscope, you obtain granulars that look like this. And if you move it according to a hyperbolic funnel, which means it's slow at the periphery and fast at the center, you obtain a much smoother precipitation pattern, which is shown here on the right. And this is pretty similar. If you look at this particular image on the top, this is one obtained from oxygenated waters that you can buy in the shelf from the supermarket. And if you do a drop evaporation method, you end up with a structure like this, fully cracked, much more similar to that in terms of this very rude pattern that forms in the dried water sample. And this is a particular issue that I will talk about on as well. So this we skip because we don't have too much time. This particular aspect then he was using in terms of to study nature's flow patterns in rivers. And yet you can see that the flow pattern over here, he envisioned it as a circular winding pathway that gets charged, so to speak, and bends and releases energy at the straits. And then it bends or rotates in the opposite way. He envisioned that as vortices embedded in vortices, where the cooler sections are located in the center strand, and the warmer water layers are more or less circular, the outer strand. So this provided him a better understanding of how to regulate rivers and how to avoid floodings. So in regulating river in forms of straight river, let's say mechanical straighting rivers, for him was an absolute horror, and is probably also related to the problems, environmental problems that we have with inundations and high water incidents when it precipitates at a very intense level. However, he envisioned this particular vortex formation again as a self-cleaning mechanism of the river system. So if you introduce a polluted water streak, the river is able, because of this particular, let's say, vortex formation, to self-cleanse. Then, of course, we have, there's one that's keyword, the soliton effect. We have this, skip that one. The soliton effect, we're gonna maybe have time to discuss this later on because it's a relevant issue in biology, especially in blood circulation and in tree saps. But anyway, let me focus a little bit further on this particular pattern that he outlined. In order to, for example, design pipes, he came up with particle solutions and patents. So he had this particular pipe, and introduced vanes. These vanes are used to, in this particular case, you see that a little bit better. These vanes are used to direct the flow. So you generate the vortex inside with kind of secondary vortex at the periphery, kind of a bearing. And this kind of a bearing allows you to have, let's say, a sliding system within a static tube. Not at all the parabolic flow that we know from fluid dynamics. And Walter Schauberger, the son of Viktor Schauberger, then came up, well, let's test it. And we go to Stuttgart University and they did the Purple trials. And the Purple trials are nothing else. They looked at the various forms of pipes. These various forms of pipes are played straight, conical, narrowing at the very end, or twisted as this one with an embedded, let's say, helical pattern that represent the vanes. You can see it a little bit here in this particular section, how these vanes are hammered into the copper pipe. There's maybe a better representation of here. So what the fluid dynamics that they observed, this was the big aha effect. And that's what also George is working in this lab. It's a collaborator of us. And they're trying to understand how this particular effect can happen. Because if you look at the normal pipes, you have the flow velocity, and which is more or less the abscissa against the friction here up in the ordinate. And you see that the normal standard pipes behave as expected. However, if you look at the spiral winding pipes, there's certain resonance moments, but obviously friction turns out negative. So what does it mean, negative? Does it speed up? So this particular investigation generated a lot of controversy. And so far, it's still debated whether Popper made it right or wrong. That's why we want to have a better understanding by repeating this particular effect in George's lab. So the next section over here. So we come to the tree aspect, because if you look, how is a redwood in the United States, I'm particularly talking about these particular plants, 100 meter, 120 meter tall, how should they be able to suck up water from the ground all the way to the tree top, to the canopy? It's 120 meters difference height. So the standard cohesion tension theory is not sufficient to explain that. Particularly when you look at the canopy, all the leaves that are spread out, for example, in Europe, when the leaves are falling off because of winter and spring is approaching. These leaves spread out all simultaneously. There is no, let's say, lag between bottom or upper gradient. They're all present and germinate at the same time, which means the tree has an intrinsic property of sucking up the water into every aspect and every, let's say, part of the organism. And there's one thing that Schauberger envisioned, and this is a representation from Colin Coates' book, is the obviously charge gradients inside in the, let's say, sapwood or let's say hardwood section, which is the water conductive structures, the xylem structures of the tree. Yet, what he didn't know at that point is that trees enter a sort of cavitation. I'm not quite sure whether you can hear that. Let's see, can you hear that? Just wave me with your hands. Anyone can hear this cracking noise? Yeah?
No.
So we spit it out again. So which means that trees cavitate in terms, and this cracking noise is the cavitation, the water column that cracks. So how do trees fix this cavitation, this vapor that forms this, let's say, this loss of continuity of the water fluid, the fluid that actually needs to be sucked up? It's obviously able to do that. So there's a huge problem in understanding how plants work. And Schauberger came up with this particular idea that obviously fluid transport in plants has to occur in vortices, as we have seen in the previous slides in river flow or in the hyperbolic funnel. And this is still an open question because it hasn't been experimentally verified. So, however, allow me to show you this. In Jerry Pollack's lab, they're working with Nafion tubes and on polystyrene lattice spheres to see what effect does have infrared light on this particular structure. Of course, Nafion tubes have peculiar properties because they are Teflon backbones with sulfonic acid side chains. But if you place them on the microscope and look at it, you can see if there's no gradient, gravitational gradient, because the table is inclined or slanted, you have a transport. You can see this is a transporting film of PSL, polystyrene latex spheres. In this section, it's a gel. This is on the other section. This is the Nafion tube, but this is a gel. It works also with gels, and this is a hole driven into the gel where the polystyrene nanoparticles flow through it, and they're driven by light, which means light in this case pumps water, or helps the tree to pump water upwards. Yeah. There's another peculiar effect if you leave this polystyrene latex soaked soup with this colloidal structure standing for overnight, only exposed to some sunlight. You have peculiar effects like, for example, a particle-free zone. But it's an interesting paper that can be shown up that I read up in this particular reference. Why is this relevant? Because when in Romiana's group, they worked with this Haberleia plant, and they could show that what the plant does when it's getting under water stress, that's an interesting effect. You have obviously free water and bound water. And if you look at the free water, bound water bands, then you find these spectral, let's say, the interesting bands over here. However, if you look at them, what does it mean if you translate it? Then you have to see the protonated water clusters on the larger ones with the hydrogen bonded associated network, which makes them a little bit more viscous and then less fluid. So it seems that the plant is obviously able to control water losses when it gets under stress. In this case over here, you can see it literally gets under stress, dehydration stress, and only recovers later on if you can give the plant water and recovers, which means that the plant is able to control from one state to the other. And we assume that here there is coherence patterns going on. And in the last section of our talk, we're going to talk about the coherence effects a little bit more in detail, so you understand what this means and what the plant is actually doing. So it's a very intelligent mechanism in order to survive under harsh environmental conditions. I have to skip that because of time constraints. So let's go back to another peculiar, let's go forward to another peculiar effect that Schauberger found out. And he termed this as tone singing. So it's a sound and wave on water exposed rotational method that he used to, so let's say, make the water more usable. So he had, for example, if you do a clockwise turn with a stick in the barrel of water and you sing a falling pitch sound to it, like, and then you reverse the direction and then, and you do it with a very sonar voice and exhale deeply into the barrel. So all your carbon dioxide that you exhale is more or less tuned into the rotating water mass. The results are interesting. I mean, this is an effect from Hallberg, a Swedish guy, but he's also in the PKS group of the Schauberger, and using a different device. But obviously, you have effects and results in the water availability that plants can use it in terms to drive better, to develop better. And this is the setup that they were using. So this points something very peculiar, and is the polywater debacle that the Russian scientists have developed, because they found out that water at very confined spaces doesn't freeze, doesn't boil, has peculiar viscosity properties. And one such drop could immediately change the entire oceans. So this was the media hype that followed. Unfortunately, as good as the approach was and as serious the scientific investigation was, the interpretation was completely misled and completely discredited this branch of science, unfortunately. So Schauberger finally conceived a device to produce high quality drinking water in such a way as to come very close to pristine spring or wells that you found in the mountains, where you can actually drink water in very, let's say, pristine and healthy water that is available for human consumption. So he tried to repeat that by using a mechanical device. And this is one of them. So you have a cooling device, you need a carbon dioxide input, you have a little bit of minerals that you need to add in order to make this apparatus working. So you have a rotating barrel inside that creates the vortex, and you have the feeding of carbon dioxide and a little bit of minerals that go in. So this is the static version, and this is a throughput version, continuous flow system that he conceived and patented. Yeah. Okay. Okay, now we have a little bit of an interference. So, the interesting aspect why his band is doing this is that we know that water does not exactly behave the way we intend to behave. Water, for example, spring water is not sterile at all. If you look at the spring water and pass it through a flow cytometry, in this case, it's shown over here, and investigate not just the quantity, but also the quality, you realize that there is a rich biological community embedded. For example, you find in these three spring waters microorganisms in huge concentrations, so they're not sterile at all. And furthermore, what you see, if you look at the diffraction index because of the laser beam that puts on it and the fluorescence effect that it shows up, you see a spectrum which allows you to deduct a kind of richness, biodiversity richness within the particular water sample, which means you end up with an autochthonous, non-pathogenic microbiomic compositions. This is compositions that you drink when you consume this water. So when you expose the water in your pipes for household domestic purposes, for example, to additives like chlorine, fluoride, or ozone exposure to sterilize it, you ruin this particular richness. So the water becomes very, very poor. And that's the way, or that's the reason why Schauberger wanted to get this device done in order to overcome the shortcomings of modern drinking processing plants that we use in our tap water systems.
Pierre, I'm very sorry, but we're running out of time. Your presentation
how much time do we have?
Do we have time for more questions, maybe?
Yeah, I would like to go to the quantum electrodynamics, which is another 8 slides. What do you think? Let me know.
I'm very sorry, but the time is running. I don't think we have a time for 8 slides.
Because
we have a break after that, which is 20 minutes, Pierre. So if you can do it for 5 minutes, will be great.
Pierre, you are mute.
can you hear me?
Now, yes.
Okay, good. Okay, briefly. Okay, why does this matter? And we think that Schauberger came up with a very interesting concept that is related to the coherence principle of quantum electrodynamics. When Preparata and Garbelli perceived that coherent structures are present in ice crystal-like structures, and we know there are there, but if coherent structures are present also in the liquid phase, like here, or above 300 Kelvin, and even the gaseous phase, this is something new. And what does it mean? So it means that the degrees of freedom of the population of the molecules of water highlighted as m, and the phase correlation angle as phi is greater than half, which is a dimensionless unit, means that they align like this. So this is the classical coherence concept, and this can be shown in this particular video. Then you use metronomes that are kicked in, and certainly they align into coherence because of a coupling medium underneath. Now they're completely coherent. So this is a 32, let's say, molecular structures in this concept with a phase angle that approaches almost zero. There's no phase differentiation between these two. So it's a case-scale property, which means it's fractal. And how is this possible? This is possible only if you look at the excited state of the oxygen orbital, which is this particular energy band of 12.6 or 12.7 electron volts. you pump in photons, you charge the system, it becomes excited, and then it releases, relaxes again, and releases a photon. So when you look at the particular spectra that have been accumulated in permittivity of pure water, and this is the various works from Cazzi and Antonello Denigno, and we know we can find the classical ones with the dielectric constant of 80 of water, which is here, but we also see a coherent one, which is above 80, and we see also a non-coherent one. So if you mix them up, you come pretty much close to here. I'm not talking about what needs to be done in order to get it matched also in the terahertz spectrum, but what Antonello found out is if you look at the infrared spectrum that you measured over here, and you deconvolute the spectra, you find 3 bands that all taken together form up the, let's say, the enveloping form of the spectrum. And if you allocate this, you can see this particular band closely matches with the water vapor spectrum. This much better fit here with the liquid phase, and this is a very good fit with the icy phase, with the crystalline phase. So we have a 3-phase system in the liquid system, which corroborates again the work from Preparata. And this fits again also to the aquagrams that we have heard already in the last days. So this is, I think, the most crucial aspect here, because this you have the photon trapping, the exchange of photons within the water molecules that form up a coherent domain, a cluster. And this particular cluster is only possible because you flip from the sp3 hybridization to the 5p hybridization of the oxygen molecule. You change from the ground state to the excited state. However, the perturbative ground state in non-coherent system is a little bit higher than in coherent one. So coherent is a more attractive state. And if you look at the energy difference here of 0.26 electron volts, it's a lot more stable than the thermal assault at room temperature, which is only 26 milli-electron volts. So you cannot disturb this coherent structure when using thermal energy. And this, of course, brings me to this particular aspect, because now you can, not talking about too much about it, only let me say this, that you have the quantization, which allows you in the kilohertz range to have mesoscale organization, and in the hertz range, the steps in between still quantized in the hertz range. So now you can scale it up from the nanoscale to the mesoscale to the microscale, macroscale, and the gigascale, whatever you think. So, and this works because water is able to switch protein activity. And as with the presentation from Michael, we know that microtubule assembly is still a mystery. However, if the mystery can be unsolved using this particular approach, then we immediately have to think about Gilbert-Link's association induction hypothesis, where the protein functions only when water is in the decoherent phase. So you have to have the decoherent phase along with the coherent phase. And if the water becomes coherent again, it inactivates, it straightens out the protein, so there is no protein activity. You switch it on and off. So this particular device up here allows you to measure that. It can be read up in this particular paper. So in order now to understand the working principle from the nanoscale to the macroscale and megascale, so we have coherence domains that consist of many, many molecules, millions of molecules that build up the coherence domain. And supercoherence is built up when you have many, many coherence domains, and better, well, coherence domains exclude dissolved ionic species, so they're on the surface. And they are crucial because they are providing the macroscopic coherence effect is needed in biological tissue at room temperature. So, and now I'm almost done. This particular stuff shows you when the coherence domain attracts on the surface, due to the resonance, two species, brings them together and reacts them. The product then in turn changes the resonance frequency of this coherence domain again, which attract different species. So you have different species that react together and form a product. And this in turn alters the coherence frequency of the frequency of the coherence domain again, forming a third one. So, and the pathway goes on with this. It's a classic example of the Calvin, of the citric acid cycle. And the reason why this is working, as shown below here. You have in if you use the Maxwell equation and you look at it carefully, you see that the voltage potential that is a scalar entity is correlated to the phase angle, whereas the vector potential A also shows a relation to the phase angle. So the trapped voltage potential inside the trapped photon field in here cannot escape. It's a virtual photon. However, the vector potential exceeds well beyond, and this is the reason why this particular ionic species at the outside can act and interact and form a, let's say, a functioning metabolic system. And this is the last, almost the last one. Yes. So
yeah, I don't know if we still have a time. I think it's time to end.
Yes, I'm okay. I'm done. More or less, the basic principles are explained, and I don't want to add anything else unless, except that this particular coherence is able to propagate into supercoherence from the microscopic level, molecular level to the social level, so to speak. Yeah. And if you consider n, the number over here, and not the mass as outlined here in this particular sketch, then you always amount to properties of water molecules that sheerly outnumber the dissolved biochemical species. And with that, I think I have to wrap it up, although it's maybe a little bit choppy in my presentation because of lack of time. But as I said, Schauberger, Reich will be next time. And concerning Romiana's retirement, I don't think she will retire at all, because this is something that she now can do and pursue what always has been interested in her term. I would say the most fruitful period of her life is now just in front of her. Okay. So with that, I close it. Thank you for your attention, and sorry for having a little bit and being interrupted also with the kids, but it's early morning here and my other half is gone for work. So thank you for your attention. Open for questions.
Thank you.
I think that you need to move with the questions to the chat. And thank you everybody for very nice presentations. I hope you all enjoy it. And if you have any questions, please write this in the chat and Pierre will gladly answer to you. And
I've seen it, yeah.
Klaus. Thank you.
Oh yeah, there's a huge list of questions.
Yes. Thank you very much, Pierre.
Okay, thank you. So,
yes, we need some time to swallow. Yes.
Yes, I know. Well, as I said to Yelena, yes. I forward you the presentation so you can digest on it.
Yes.
And later on and find the references, the links for the videos, and so you get a much more concise picture.
Yep.
I just want to say half a minute. Maybe it would be, I saw your presentation and it was fantastic. I connected it to many of the things that we work on, but it was different when you spoke. So maybe you could make a video of the second part of your talk. I mean, we have a film, so we could have it for the, I would love to hear it. Or if you have a...
Well, if we can do this together, I mean, I explain it to you and you record it and you have the film already, but then we do it offline in a private setting and you post it online.
Yes.
Well, maybe it would be nice if we can have a webinar or discussion like yesterday.
Absolutely.
I think it would be.
Yes.
Yeah.
Great.
So let me know when you want to do this, because then I can show you what happens if you look at this in real world conditions. Can you see this?
Yeah.
This is water, pure water, which is no longer liquid. It's gelidified.
Yes, gelidified.
This is an iterated naphthionated sample of water from Elias' lab. And this is, look at this.
Honey.
It's honey. Yeah, it's honey, but it's 60% water and 30% rapeseed oil.
Wow.
Wow. Wow.
Okay. So this is just a perspective of what can be done with Schauberger and using quantum electrodynamics.
Everything can become something else.
Yes. Okay, let's leave it like this. We get together on a private setting and try to elaborate the second part of the talk in such a way that you have a much better understanding.
Thank you. Thank you so much.
And you let me know when we can do this. So I leave the organization of the stuff.
Yeah.
Yes, we will.
Perfect.
Thank
Let's
you.
do it this way.
Thank you.
Bye-bye. So we have a...
Thank you. Bye.
Justina, thank you so much.
Ciao.
Hi to kids. Ciao, ciao.